Have you ever stopped to think about what pushing a heavy box across the floor has in common with, say, landing a perfect kickflip on a skateboard? Well, it turns out they're connected by these incredible, invisible forces that run our universe: work, energy, and power. And today, we're going to break down what they are, because they're not just words in a science book. They are literally the language physics uses to describe motion and change. Let's get into it.
So, seriously, what is the link between the grunt work of shoving a box and the free-flowing thrill of riding a skateboard? I mean, one feels like a chore, the other feels like flying. But you know what? In the world of physics, they are two sides of the very same coin. They're both playing by the exact same, really elegant set of rules. Just look at these two pictures. On the left, you've got pure, simple force making something move. On the right, you have this beautiful dance between height and speed. But at their core, both of these activities are all about one thing: moving energy around. And that is where our whole story really begins.
Okay, so let's tackle our first big idea: work. Now, we use that word all the time, right? I've got so much work to do. That was hard work. We think of it as just effort. But in physics, the word work has a very, very specific meaning, and it has a lot less to do with how tired you get and a lot more to do with actual movement.
Here's the deal in physics. For work to happen, two things absolutely have to be true. One, you apply a force. And two, that force has to make the object move. So, picture this. You could spend all day pushing against a solid brick wall with all your might. You'll be exhausted, you'll sweat, you'll feel like you've worked. But if that wall doesn't budge one single inch, then in the eyes of physics, you have done exactly zero work. Crazy, right?
And this is the super simple formula that puts it all together. Work, that's the W, equals force, your push or pull, the F, times the distance the object moves, which we call S. That's it. It's this beautifully simple idea that just unlocks a whole new way of looking at how things get done in the universe.
All right, let's make this real. Let's say you push this box with a force of 100 newtons. That's just the unit we use to measure force. And you manage to move it 5 meters. You just multiply those two numbers together. 100 times 5 gives you 500. And the unit for that work is joules. Now, you're going to want to remember that word, joule, because it's not just the unit for work. It's the currency for something even bigger: energy.
Okay, but let's be honest. The real world is rarely that simple. We don't always push or pull things in a perfectly straight line. So what happens when you're pulling something, but, at an angle? Does that change how we think about work? Oh, you bet it does.
So take a look at this. You're pulling a box with a rope, but notice how the rope is angled up? The box is moving straight ahead, horizontally. But part of your effort is actually pulling the box upwards. So the real question is, does all of your pulling force count towards the work being done?
And here is the super clever way physics handles this problem. We basically pretend that your angled force is split into two parts. There's a part that pulls the box forward, the horizontal part, and a part that pulls the box upward, the vertical part. Now, since the box isn't flying up into the air, that upward pull isn't actually helping it move forward at all. So it's only the forward pulling part of the force that counts as doing work.
So how do we fix our formula? We just add one little thing: cosine of theta. Now, don't let the trigonometry scare you off. Cosine is just a super handy math tool that helps us figure out exactly how much of our force is actually pointing in the direction of motion. Think of it like a filter that gets rid of any wasted effort that isn't helping to move the object forward.
Let's see it in action with this toy car. We're pulling with 10 newtons of force, over 5 meters, but at a 30-degree angle. Now, if we were pulling straight, 10 times 5 would be 50 joules of work. But when we plug that 30-degree angle into our new formula, we only get 43.3 joules. See? It's less. Because of that angle, some of our effort isn't contributing, and we're not getting the full bang for our buck in terms of work done.
So, we can calculate work, even with angles. But what's the big deal? Why do we care so much about this calculation? Well, because work is how we transfer the most fundamental thing in the entire universe: energy. Think about it this way. If energy is money, then doing work is the act of spending it or giving it to something else.
And that brings us to one of the most important bedrock laws in all of science: the law of conservation of energy. It's a simple but profound idea. It says you can't make new energy out of thin air, and you can't make it disappear. You can only move it from one place to another or change its form. So when you do work on that box, you're not creating energy, you're just taking energy from your body and transferring it into the box. The total amount of energy in the universe is always the same. It's just constantly changing hands and changing forms.
Now, this energy comes in a bunch of different flavors: heat, light, chemical, but for what we're talking about today, we really only need to focus on two main types. I want you to meet the dynamic duo of mechanical energy: kinetic energy and potential energy. The difference between them is actually pretty straightforward. Kinetic energy is the energy of things that are moving. Potential energy is stored energy, energy that's based on an object's position and is just waiting to be used. It's kind of like the difference between a car speeding down the highway and that same car parked at the very top of a steep hill.
So let's look a little closer at kinetic energy. The formula is 1/2 times mass times velocity squared. Now, the most important part of that formula is the v squared. You see what that means? It means that speed, or velocity, has a huge impact on kinetic energy. If you double your speed, you don't just get double the energy, you get 4 times the energy. And that right there is why even a small increase in speed can have such a massive and dangerous impact in something like a car crash.
And now for its partner, potential energy. The most common kind we run into every day is gravitational potential energy. So when you lift a heavy book off the floor, you have to do work against gravity, right? Well, that work you did doesn't just vanish. It gets stored in the book as potential energy. The higher you lift it, the more work you do, and the more energy you pack into it, just waiting to be released.
Okay, this is where it all comes together. Let's go back to our skateboarder on the ramp and watch this amazing energy exchange happen in real time. This is the magic of physics, this beautiful, constant dance between potential and kinetic energy.
Picture the skateboarder at the very top of the ramp, just for a split second, totally still. At that moment, they're at their highest point, so their potential energy is maxed out. But since they aren't moving, their kinetic energy is 0. All of that energy is just stored up, like a compressed spring, ready to be let go.
And then they drop in. As they roll down the ramp, gravity starts to do its work, cashing in that stored potential energy and turning it into the energy of motion. As their height goes down, their speed goes way up. By the time they reach the very bottom, they're at their lowest point, and pretty much all of that potential energy has been transformed into pure, fast-moving kinetic energy.
And here's the absolute coolest part. If we lived in a perfect world with no friction, the total amount of energy, the potential plus the kinetic, would stay exactly the same the entire time. As one form of energy goes down, the other form goes up by the exact same amount to take its place. It's a perfect trade. So, let's put the whole story together one last time. Step 1. It all starts with work, which is just a force causing something to move over a distance. Step 2. That work is what transfers energy into an object. And step 3, once the object has that energy, it can transform back and forth between potential energy, the stored kind, and kinetic energy, the moving kind.
But that leaves us with one final big question. If energy can't be destroyed, why does our skateboarder eventually slow down and stop? Where did all that kinetic energy go? Well, the answer is friction and air resistance. The work done by friction doesn't destroy the energy, it just transforms it into other forms, mostly heat in the wheels and the sound of the board rolling on the pavement. The energy is still there, it's just been spread out. And that, right there, is the incredible story of work and energy, playing out all around us, in everything we do, all the time.